Today we will study about discrete random variables. This will be the first part of two videos. Let x be a random variable that is a function from S, the sample space of an experiment, into the set of real numbers. Script x is going to be the set of values or the image of x. When talking about random variables, we will often be only concerned with the image, that is, the values of x, and not necessarily worry about what the actual experiment or the sample space S was. Now, if capital F sub x is the CDF of x and P sub x or F sub x are the PDF or the PMFs of x, we can use these to calculate the probability that x lies between A and B, right? That is the probability that x takes values in the interval A comma B. X is said to be a discrete random variable if the CDF, the cumulative distribution function of x, is a step function. In this case, script x, the set of values of x will be a discrete subset of R. That is to say that a script x is either going to be a finite set or a countably infinite set. In the case of finite sets, it means that it's going to be in bijection with 1, 2, 3 up to capital N for some fixed capital N inside the set of natural numbers N. On the other hand, countably infinite sets are sets that are in bijection with the set of natural numbers. The goal for today is going to be to study random variables which have a finite set for its set of values. That is, we'd want to calculate the PMF, P sub x, the expected values, and the variances of such random variables. The first random variable would be the uniform discrete random variable. We will fix a capital N inside the set of natural numbers. Then the random variable x has a uniform discrete distribution with parameter capital N if the set of values script x of this random variable is the set 1, 2, 3 up to n. Furthermore, for any x inside script x, p sub x of x is going to be equal to 1 over n uniformly. Note that if we take the sum over all values of x inside script x of p sub x of x, you get n times 1 over n, which is equal to 1. Also, p sub x of x equals 1 over n, which is a positive number for all values of x. So this tells us that p sub x is a legitimate probability mass function. The distribution table for x is computed as follows. We have the values of x being 1, 2, 3, 4, all the way up to n, and the probability that x equals x is uniformly equal to 1 over n. In this setting, the expected value of x is calculated using the formula for expectation. And in the process, we use the formula for the sum of the first n numbers, which is going to be n times n plus 1 divided by 2. And when we divide out by n, we will get the expected value, which is going to be n plus 1 over 2. To calculate the variance, we are going to use the property that the variance of x is the expected value of x squared minus the expected value of x squared. Working through this, we notice that the expected value of x squared is going to be n plus 1 times 2n plus 1 divided by 6. And plugging this into the formula for variance, that is expected value of x squared minus expected value of x the whole squared, we notice that the variance becomes equal to n plus 1 times n minus 1 divided by 12. We also note that if a1, a2, a3 up to an is a subset of real numbers, we can define a function h from script x to a1 through an where I goes to ai. Now if x has the uniform distribution, then the expected value of h of x is going to be equal to a1 plus a2 all the way up to an divided by n, which is exactly the mean of these n numbers, and the variance of hx is going to be the variance of these n numbers. In this setting, we get that the uniform discrete distribution just gives us the regular mean and the variance of a set of n numbers coming from the set of real numbers. Now, fix capital N, capital M, and small n to be natural numbers. And suppose a bag has capital N balls, identical in all respects except for color, and M of these balls are red in color. An experiment consists of choosing N balls from this bag. And if we set the random variable x to count the number of red balls in a sample of small n balls, we want to be interested in calculating the probability mass function of this random variable. However, notice that this depends on how we sample, whether we are sampling without replacement or if we are sampling with replacement. When we are sampling without replacement, the distribution of this random variable is going to be what is known as the hypergeometric distribution with parameters capital N, capital M, and small n. When we are sampling with replacement, we are going to get the binomial distribution with parameters small n and p equals capital M over capital N. There is a typo in the video. It should have been p equals capital M over capital N. We now talk about the hypergeometric distribution. The random variable x is said to have the hypergeometric distribution with parameters capital N, capital M, and small n if the random variable takes values in the set 0, 1, 2, 3 up to n, and the probability mass function is defined as follows. P of x equals x in this case gives us the probability of getting x successes in a sample of size n sampled without replacement from a population of size capital N with m successes. Note that implicit in this discussion is that capital M has to be less than capital N, that x must lie between the maximum of 0 and small n minus capital N plus m and the minimum of small n comma capital M. We now note the expected value and the variance for the hypergeometric random variable. If x has the hypergeometric distribution with parameters capital N, capital M, and small n, then the expected value is going to be equal to n times m over capital N, and the variance is going to have the following formula in terms of capital N, capital M, and small n. Note that if we set p equals capital M over capital N, the expected value of x is going to be n times p, and the variance of x is going to be n minus small n divided by capital N minus 1 times n times p times 1 minus p. We next talk about the binomial distribution. We will say that the random variable x has the binomial distribution with parameters small n and small p if the set of values equals the set 0, 1, 2 up to n, and if for any x inside script x, the probability of x equals small x is going to be equal to n choose x times p to the x times 1 minus p to the n minus x. This is called the binomial distribution because we use the binomial formula to show that p sub x is in fact a PMF, that is a probability mass function. When working with the binomial distribution, n is typically going to be the size of a sample, and p is going to be the probability of getting a success on every trial. So if x has the binomial distribution with parameters n and p, then the expected value of x is going to be equal to n times p, and the variance of x is going to equal to n times p times q, where q equals 1 minus p. We finish up with a discussion about Bernoulli trials and the Bernoulli random variable. An experiment in this setting is going to have exactly two outcomes, a success or a failure. And if p belongs to 0, 1, then we will let the probability of a success to equal p and the probability of a failure to equal 1 minus p. X is a Bernoulli random variable with parameter p if the values of x lie in the set containing 0 or 1, and the probability mass function is defined as equal to p if x equals 1 and p sub x of x equals 1 minus p if x equals 0. Note that in this case, we will have the expected value of the random variable to equal to p and the variance to equal p times 1 minus p. So we have spoken about the uniform discrete random variable, the hypergeometric, the binomial, and the Bernoulli random variables. These are some of the most common discrete random variables with finitely many values that we will come across. We will talk more about these in future videos, but this is all for now. Take care of yourselves, and I will see you around.